Now we're ready to learn how to create that executable program. We're going to see that we're going to run some software that's going to take care of the pre-processing, the compiling, the linking, and the execution. We need a C compiler in order to take the program source code that we just wrote here. We wrote in that text editor. We need to be able to turn that into a set of executable instructions that our computer knows how to run. We're going to use the CodeBlocks IDE. Remember, IDE stands for Integrated Development Environment, and its suite of tools in order to create that executable program. Whenever we write source code, we always then have to turn it into that executable, and there's a series of steps that occur. Pre-processing is the first step, and what it does is if we've got some pound includes in there like we do, it actually goes ahead and pulls that information and adds it to our C program. Later we'll learn how to put macros and other things into our program and talk about what that does. After the preprocessor step, the compiler takes all of that source code and checks the syntax. So it's basically checking to see if we've conformed to the grammar rules of the language. If we have not, it's going to generate some errors. If we have conformed to those grammar rules, it's going to generate assembler source code. Assembler source code is closer to the machine language, not quite what the machine needs yet. After that, the assembler then goes ahead and takes that assembly source code and produces a listing that it needs to create an object file. The object file is then fed into the linker, and the final stage then, if we have some other libraries, special libraries that we need to link against, then that code from those is pulled in there. But finally, our final step is an executable file. We don't have anything to link today. Later, we will learn about linking libraries. So what we want to do is we can visually look at this. We can see that we always start with the C program source code. And then after we get that code, in order to turn it into this executable down here, we have to have the preprocessor program run, the compiler program run, the assembly language program to generate the assembly listing of object code in this case. And then if we have other libraries that we link to, later we may link to some math libraries, that will go ahead and link in that code and finally generate our executable program. Our executable program is the one that's going to run. Right. So we're going to go ahead and use CodeBlocks to create our executable today. If you haven't already installed CodeBlocks on your computer, you should do so if you want to follow along with this. CodeBlocks works really well on Windows and Linux. It doesn't currently work as stably on Mac. So if you want to go ahead and use CodeBlocks on Mac, you can try that. What I'd recommend, what you have to do in order to use CodeBlocks on Mac is install Xcode from the App Store. If Xcode has its own compiler, its own GCC compiler it's going to bring in, and that's why you need that for CodeBlocks. If I had a Mac, I would probably just go ahead and use Xcode for all of my coding. And later we'll also learn to code from the Unix command line, so I would do that. Like I said, if you want to go ahead then and try installing CodeBlocks on your Mac OS X, go ahead, but you have to install Xcode first and then CodeBlocks next. All right, what we want to do is we want to create a CodeBlocks Hello World project. Right? It's actually then going to take our own executable code. So what we wrote in Notepad, we actually need to get to a compiler. Let me go ahead and bring up CodeBlocks here. All right, so I told the computer to start CodeBlocks, and when it comes up in this environment that asks me if I want to create a new project or open an existing project. What I want to do today is create a new project, so I'll just click on that. And if I choose right here, console application, say go, what I want to do is, CodeBlocks works for either C or C++. We're working with a C language, so we want to choose C. Click on next, and now I need to give this project a title. So I'm just going to call this hello. And by default, this CodeBlocks is set to save this on my desktop. That's fine with me. It's going to create a folder called hello. It'll create a CodeBlocks project file within there. I'm just going to click next to take that default. If you want it to save it elsewhere, you can go ahead and click on that and navigate to wherever you want to save it and make any new folders you want. Like I said, I'm just choosing next here. All right. By default, I've already chosen that I want the compiler that came with my code blocks installation, this GNU GCC compiler. I'm going to leave these checked, creating the debug configuration, the release configuration. We're really only worried about the debug configuration in this class. By default, these are checked. I just leave them this way, and I'll click on Finish. All right. Now, it actually created a program for me, a project environment. What I want to do is down here in the Project tab, see this folder called Sources. If I open this up, it actually created a file called main.c. So I'm just going to double click that to open it. So whenever you select the console application, CodeBlocks goes ahead and creates this basic file for you. Now, it always includes the standard library that we don't need. So I'm going to delete that. So I want this to look like our code. So we've got pound include standard.io.h. We need that, remember, for the printf function. It gives us our main, so int main. We can have the word void here, or we can leave this empty. Gives us our starting curly brace, our ending curly brace. And by default, it always puts a printf hello world statement in here. And then a return 0 statement. So now I'm going to hit Control S just to save that change I made. Now I can use these tools to build my code. If I want to, I can go ahead here and say compile. So I go to build, compile, current file. And when it does that, it goes through and checks the syntax. And it displays some messages down here in the build log. So what it did is it actually ran the GCC compiler. I've got some warnings enabled in here by default to let me know if I violate any of these rules. And I've also told it to use the C99 compiler in here, but it just goes ahead, it knows its path to where these programs are, and then it compiles it against here. My project on the desktop, my folder hello, my file main.c. It creates some compiler symbols in for my object file. But what I'm really worried about is I usually don't pay attention to this. I want this information right here. 0 errors, 0 warnings. I don't want to proceed. I can't proceed if I have an error. It will not build my executable. If I have a warning, I want to go back and correct that. Technically, I can build my executable with warnings, but I prefer to always get rid of any warnings. So you're always looking to do the compilation step first, like we just did. Remember, we did build compile to generate that. I'll escape there. And once we do that, if we go out and look where this is saved, so remember I saved this on the desktop. It should be in a folder called hello. Here it is, hello. What it did inside of here, see this project, hello.cbp. CBP stands for Code Blocks Project File. That's not a C file, that's a code blocks thing. Here's my C file. Here's that main.c. So remember the .c extension is for C source code. It then created a folder called obj for object, one for debug for the debug environment, and it went ahead and created a main.o and a main.list. So let me go ahead and show you what the preprocessor files look like and what the list files look like. Let's go back to our slideshow here. Right, and here's where we left off with this console application. We went ahead and compiled the program. And what happened is we generated a file called main.o. What I've done is within these lecture slides, I've given you this preprocessor main.o file. I renamed main.o to preprocessor main.o. And if you want to go ahead and open that up, you'll see that you have the source code listing that has a lot more information in it than what your original source code did. If I go, okay, that's my object file. Let me go. You need what you actually need is a special command in order to get the preprocessor listing. I'm going to right click and edit this with Notepad, and when I open this up, this is actually after the preprocessor step. So all of this, starting here with line 1, related to my computer, was added by the preprocessor. All of this information here, this structure information, none of this you should be worried about making sure whether you understand this or not. But here it added some information about printf. Basically what it did is it pulled a lot of information out of the standard IO library. We're not using fprintf, we're not using sprintf. We need this information for printf. So when we said pound include standard IO.h, it brought in a lot of information from there and added that to our source code. If we scroll all the way down to the bottom, quite a ways, if we scroll all the way down here, look, line 278, here's our original code. Int main, curly brace, printf, hello world, return 0, ending. So all of this above was added by the preprocessor. Now we'll just be grateful that the preprocessor does that for us and we don't have to write all that code. We want to keep things simple like this and use the tools that we have. If we go back then as well, besides the preprocessor step, we said after compilation that there's an assembly step. So here we started with our source code, the preprocessor program written, the compiler program, these are software programs. The assembly language, this generated an assembly language program. So the compiler generates this, which gives us this listing. So once again, I've had to put in a special code in order to get this out. But if you want to go ahead and open up main.list that was given with this, you'll see a lot of extra code in there. And that's the assembler code. Finally, the assembler code will be turned into object code, but we have to complete that step. Here's an example of main.list of if you ran all of that, you would get a lot more. Actually, these are all directory path names. You would start getting information related to assembly code. Assembly code is a whole different set of instructions. We won't be writing assembly in here this semester, but if you're curious about some of the code that you would get, you can see what the assembly listing looks like. All right, let's close this down. Let's go back to code blocks. What we did here was we did build and compile. Now, if I was to say compile again, I get a message saying nothing to be done, all items are up to date. If I make changes in my program, then I have to go back and recompile. But the program is smart enough to know that I haven't made any changes, so it doesn't recompile. It just tells me nothing to be done. Now, what I want to do is I want to run my executable. So when I'm done with the compilation step, I then want to go to build, and actually I'm just going to choose build and run. So what that does is that performs the linker step for me and creates my executable file. And then the run instruction says to go ahead and run that executable file. So notice now this window popped up. This is called the console terminal window. Here's my message, hello world. So letter for letter, it printed out. I have this extra space here because of that \n, that new line character. And then code blocks just gives me this message that says my process. So a process is running on a CPU, central processing unit. When I ran this program, it ran a single process. And it said that this process, when it ended, returned 0 to the operating system. So if I were to change that return 0 to another number, you'd see that particular number popping up. This is a hexadecimal value of that number. Gives you a little information about execution time. The nice thing about code blocks is it keeps this window open. See this message that says press any key to continue? Well, when I'm done looking at the program output, now I can just press any key. The window shuts for me. I had some message down here about the fact that this executed and the process terminated with status 0. If I wanted to run this program again, I don't have to rebuild it. I could just simply come here and say run. Once again, I get the same result. We're going to get the same result every time. We're just going to get the message hello world displayed on the screen. Let's minimize this. And let's go back to our slides. All right. Now, there is a .o file that's generated after the assembly step. And if you open that up, it looks like this. It's really nonsense that we can't understand very well. It actually tries to take code that has special meaning to the computer and turn it into something that's readable by a human. But this we just tend to ignore. It doesn't mean anything to us. What we do want to do is go out and look at the executable program. What that build step did is it generated a file called hello.exe, which is out in bin, standing for binary, and then in the debug folder. And we use the run command to actually run this file. But if we go back, so let me minimize this, and let's go back here and open up this folder, hello. Well, now we've got this bin. Bin stands for binary. Everything on your computer is a set of binary instructions, zeros and ones. So the executables are a set of zeros and ones that your processor can understand for the machine instructions. Created a debug folder, and within here, here's my hello.exe. Now, if I were to double click on this, what it does is it actually ran my program. Did you see that pop up? That's not very user friendly because it pops up, displays the message hello world, and closes instantly. We can't tell what our program's done. But we really don't want to run from here. We just want to look and see that this file was generated. Right? We want to go back into code blocks if we want to run our program and click on run so that this console terminal window stays up and we can see what happened. And when we press any key to continue, our program closes, our running instance of our program. All right, so we run from code block so that we can see that. Right. And you can see once again, we got our message there when our program executed. All right, now that we've completed our first C program, I want you to go ahead and go through the summary information. Here's some important information you should take away from this lesson. I want you to remember that programs are written as solutions to problems. Step 1, always define the problem first. Step 2, create an algorithm to solve the problem. Step 3, write program source code to implement the algorithm. I will emphasize this in every lesson. The importance of solving a problem can't be overemphasized. If you don't create that algorithm first, you will take many, many times longer to write a program. You may even get a running program. Chances are it won't be as efficient and it might be subject to runtime errors. Runtime errors means your program's running. There were no problems with the C syntax. You didn't violate the language rules, but it may not be doing what you expected it to do. So once again, solve the problem first. Create an algorithm to solve the problem before you ever write source code. You will save yourself a lot of time, a lot of headache. You'll do better on your homework. You'll get better grades. You'll get better grades on your quizzes and tests. I can't overemphasize this. Right. Also, you should take away from this the general form of a C program. We want to remember that each C program has one and only one function named main. As we start learning to write C programs, it will be a little while before we write our own functions, but we'll always be working with main in the beginning. So remember, program execution starts with the first statement in main. Remember the general form of a function heading. Remember that a function heading always has a return data type, a function name, a left and right parentheses indicating the parameter list where there can be 0 or more parameters in this list. Remember that when you're using the printf function, you have to include the library file standardio.h, where that function is defined. Also, I want you to remember that all your tests and quizzes in this course are handwritten. So what you should do right now is practice writing the Hello World program with pencil and paper. Don't type it, write it with pencil and paper to see how long it takes you to do this. And you should get it down to where you can do this very quickly from memory because you're always going to follow this general form. So be ready and know how to write the Hello World program without looking it up. You need to look it up at first. Keep practicing until you no longer need to look it up. And then I've given you a series of practice problems. Based on what you've learned today, You could go through and solve these different problems. You could write a C program that writes your first and last name on the same output line. So here's my first name and my last name on the C output line. You'll get a result similar to this, but with your name. Practice problem 2. I want you to write a C program that writes your first name on one line. So here's your first name on one line and your last name on the second line. Right? Remember, what you should do is go ahead and create an algorithm to do this. Go ahead and write your series of steps first, and then write your program. Practice problem 3. You're going to write a C program that writes your first name on the first line, skips 2 lines, blank line, and write your last name on the fourth line. Right? So write the algorithm for that, and then write your program. See if you get similar output. And then for a challenge problem, I want you to create a C program that displays this pattern. Right? This can all be done with the same program form and the printf statements that we learned. You might need more than one printf statement. You can have multiple printf statements in your program. Let's take a look at how we do multiple printf statements in our program. So let's go back to our code blocks project, and let's see how we could write print hello and world on separate lines. Let's change this. Remember that if we do a /n, that says go ahead and move the cursor down to the next line. Now I'm going to have printf. I'm going to have 2 calls to printf. So when I use a function here, I'm calling the function printf. That's the terminology we use. We say here we call the function printf. We pass it the string literal hello. Here I'm going to go ahead and pass it world. And I'm going to compile this. Good. No syntax errors. I'm going to do a build and run. And look, here's hello on one line and world on another line. So hello, this printed out HELLO. The /n said go ahead and move the cursor down to this line. And then the next time you print something, which is the W in world, start printing it on the second line in the leftmost position. So it always starts on the first line, leftmost position, and starts moving across. Then on this command /n, called an escape sequence, says a carriage return new line, so move the cursor down here and start writing here next. So we got our WORLD, our world, our exclamation mark, the /n then said go ahead and move the cursor down here if we were going to write anything else. So you could see then, and I'll just go ahead and press any key to close that window. We ended up with hello world on the separate line. We could also change this, and we could get hello world on 2 separate lines with 1 call to print out. We could make our string look like this. So our string literal still hello, /n, no space. So /n says go to the start of the next line and then start writing world. So I'm going to say build, I'm going to say compile, and then build and run, and then we got the same results. Well, there's multiple ways to write programs to achieve the same results. Sometimes one way is more efficient than the other, right? There isn't always a right way. Sometimes there's a more efficient way. There's always multiple ways to solve problems with the language, right? Normally there's multiple algorithms to solve a problem as well too. There's not always one right algorithm. Right, let me show you one last thing here, and let me show you a syntax error. What would happen if, let's see, I told you here, my printf statement is a C programming statement. It's a function call. It needs to end with a semicolon. So what I did was I just removed the semicolon. Now I'm going to say build, compile, and now I get some error messages. Let's look here. In function main, error, expected semicolon before return. So if I double click on this, notice it's showing me in red. It says expected semicolon before return. So it means before this statement, it should have had a semicolon ending a statement. So if I look here and add my semicolon back in here, and now if I recompile, notice the error's gone away. 0 error, 0 warnings. I want the 0 error, 0 warnings. Let's look at what happened if I didn't include the library. What if I left out the pound include here? I'm going to say build, compile. All right, I want to pay attention to this. So in function main, warning, implicit declaration of function printf. That means I forgot my pound include statement. It doesn't know where this function was defined or declared. If I go back now and put the pound include back in, build, recompile, that warning goes away. But when you turn in your homework for this class, you should never have errors, you should never have warnings. You should always get past the compilation errors, and you should have 0 warnings. We'll talk about that in more detail later. So now, don't forget, go back out, study the points in the summary, try these 3 practice problems, and try the challenge problems. But that's it for your first lesson on creating your first C program.